a research hydrologist and, to use a big word, geomorphologist, meaning I study rivers. And I work for you. I work for the research branch of the U.S. Forest Service. I'm assuming you're going to deal with this, George.
Yeah.
I work for the research branch of the U.S. Forest Service in Corvallis, Oregon. And I have the great good fortune of getting to study rivers for a living. My earlier life was as a river guide. And as every river... How many river guides are there out there? Just raise your hands, just out of curiosity. Okay, good. As every good river guide knows, one of the most usual questions you get asked, along with how deep is the river, is what do you do in the wintertime? And I never had a good answer for either one of those two questions as a guide. So I discovered that if I studied rivers, which basically would help me understand how deep the river was, I would also have an answer for the question of what I did in the wintertime. So that's basically what I did. And I've had truly the great fortune to have studied a lot of rivers, but my home waters, in every sense of the word, is the McKenzie. I even own a little bit of property here, which puts some skin in the game. And I'm delighted to be here to talk to you about a subject which is near and dear to my heart, and hopefully is at least of interest to you as you eat your French fries. I'm going to do this. I give a lot of talks, give a lot of science talks, and my general inclination when talking to audiences that are not, with people with a zillion letters after their name, is to not pull any punches. My experience is that if done carefully, everyone can understand the stuff. It's accessible to all. And if you don't understand it, if it doesn't make sense, please do what you did in school and raise your hand, because it means the person next to you is also going, what the hell is this guy talking about? And I'm more than happy to take the time to explain it. It's going to be a bit of a journey. You have to sort of buy into it, at least to some degree. If you need to leave, feel free to do so. I won't be offended. If everyone leaves, that's okay. I'll talk to the dogs. I've done that before. And but seriously, if you don't, if something shows up that doesn't make sense for you, please let me know. Can you all hear me all right? Is the PA? I mean, it's making little whiny noises. But is it okay? Okay. So my subject tonight is how to get this onto the screen.
There you go.
Oh, hold on. My computer did its usual thing. You can all watch me put my password in. There we go. Here we go. All right. So what I want to talk about tonight is a subject that I'm guessing most of you have heard about. Some of you have probably thought about. And those of you who are working on the river or the natural resources are concerned about. And that has to do, and I'm going to try to make the case that everyone should be at least aware of what's going on, if not concerned. But this isn't a talk about concern. It is a talk about the future. And before I get any further into this thing, I want to just say something, which is, A, the climate is changing. B, it's changing faster than we thought. And that includes a bunch of people who might have known better, including me. C, we're responsible for it. There is no question. D, we need to move on it. And E, we can move on it. But I'm not going to talk more than that at the moment, tonight. But you can take that one to the bank. That's all. That's the science community and a lot of other people are very confident in that. In fact, it's unusual confidence. There's an unusual confidence. So I'm not going to talk about climate change per se. I'm going to talk about what it means, what the consequences are, how it's going to change our lives. And it is. It's going to really change not just, it's going to change everyone who's in this room's, life, but it's really going to change the next generation's lives a lot. And the world's going to look different to them. And so it is increasingly important that we start thinking about what the consequences are. And the consequences are not universally bad, but they're different. And one of the cases I'm going to try to make tonight, in fact, is that the McKenzie River, where we're sitting right now, is in maybe, and I'm going to go out on a bit of a limb here, but I'm prepared to defend this, in the entire world, one of the most resilient places for climate change there is. And that in itself has consequences, because that will become increasingly apparent as we go. But it's bigger than you think. The McKenzie and its importance is bigger than you think. At least that's my view of it. Okay, so that's where we're going. But in order to do this, I have to sort of get everybody on the same page, which is some basic thinking about how water works here on planet Earth, okay? And I'm going to start with something that I call the big question of water. That is, if we can answer this question, we can go home. We've done it. But it's not such an easy question. The question is, how much water, of what quality and quantity, where, when, for what purpose, at what cost, now and in the future, and who gets to decide? If we can answer that question, we're done. Not so easy. And you really need, so thinking about climate, the future, the McKenzie, really involves breaking this big question down into some bite-sized pieces. And that's really what I'm going to try to do. And I'm going to start with something that, this should all be vaguely reminiscent. If you ever took a course in geography, the hydrologic cycle, how water evaporates out of the ocean and moves across as clouds and precipitates as rain and snow on the landscape, or it collects as groundwater and surface. Right, you all heard that, right? That's not the hydrologic cycle. The hydrologic cycle really is this. We start with drought. We go to panic. Then the floods come, and we get apathy until we get drought again. And actually, it's delightful because you can make the thing work either way. You can start with floods, and you can go then to apathy, to drought, to panic, so forth. So, either way, this is really the hydrological cycle. All of us have now lived, I think, through times of both drought and flood, and have some sense that how this works. But if we're going to answer the big question of water, there's some sort of basic stuff that we sort of need to paint the background here. And so, I'm not going to go into the details. I'm just going to give you the tastes of the pieces that go into it. So one question of that, how much water, of what quantity, where and when, blah, 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 is how much water falls out of the sky, right? So here's a picture of the U.S., and I draw your attention to where we're sitting in the Pacific Northwest, okay? The dark, hot pink in the upper Northwest is the most water falling out of the sky. And you will see that we are gifted here. No surprise to anyone who's lived here for any length of time. But the Northwest, extending into California and up into Washington, is really where the most precipitation hits the continental U.S. Okay, well that's all right. That's worth knowing. And the other thing I draw to your attention is that as soon as we get east of the Cascades, it is dry. Dry, 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 dry. In fact, one of the things that, if you notice, sort of right in the center of the country, there's a very distinctive line where things go from blue to yellow. That's known as the 100th meridian. And if you're ever flying across the country in a jet airplane and you happen to have gotten United Airlines to give you a window seat, you can actually see where this line is, because it's a line where you go from enough water falling out of the sky that people can grow crops without irrigation to where the irrigation begins. So it's a real line. I mean, it really makes a difference. So, but that's the amount. Then there's the question of how people use it. I mean, again, I'm breaking apart the big question. And so here's the Willamette Valley, and here's the amount of land in different classes, urban, agriculture, forest, so forth. And then here's how much water is used by those different sectors. So agriculture uses about half of the water, at least in a certain sense. I'm going to come back to this idea at the very end. We don't do a good accounting of some things like how much water do trees use. But agriculture uses a big chunk of water, even though it's not necessarily the biggest chunk of land. So that's another thing to think about. Another thing to think about is, when does the water come? And this turns out to be a big story with respect to the climate change, because when the water comes, it is likely to change, at least somewhat. And again, all of you who live here, how many of you live in Oregon? Good. How many people don't? Just so I can see. All right, some people are moving through you. Everyone who lives in Oregon knows that we're in this interesting climate where all the rain comes pretty much between October and April. But the use of water is generally maximum in the summertime between June, thank you, George, between June and May and September. So there's an imbalance between when the water comes and when we use it. And it's sort of there's an offset. And this led Mark Twain, a famous hydrologist, to comment that the solution to our water problems is more rain. I mean, that's well put, Twain. So when water comes out of the sky is important. Another thing that's important, and I think, again, this is no surprise to everyone who lives in the state, is what phase, how does it come to us? Does it come as rain, or does it come as snow? And if you're going to understand climate change, of course, you have to understand something about that distinction. So that's another thing you got to think about. So those are all background ideas. Okay, now what does the future look like, writ large, big picture? In a nutshell, what we now think for the Pacific Northwest, I'm just going to focus here on the Pacific Northwest, because all climate change at some level is local. That is, it's going to look different in Minneapolis, in Washington, D.C., in Istanbul, in Shanghai, than it does in McKenzie Bridge. But the basic story in the Pacific Northwest is that it's going to get hotter. And not only is it predicted by all the models, but all the data show it too. And it's showing it as happening faster than we thought. It's sort of at the faster end of these things. But so here is, if you look at the top part of this curve, and by the way, I apologize, you're going to see some graphs tonight. If you don't understand them, if they don't make sense to you, please let me know. I can break them down so that they're more understandable. But basically what this is showing is this is average temperature. And these are, the blue is what we've lived through. That's the historic range. And then these different bars are the ranges predicted by the different models. And the way people now, the way people do climate change is, because no one model is accurate. You don't believe any one model. But if you take a bunch of them, and they're all showing you the same thing, you have some level of confidence. And that confidence is usually expressed as a range. So that's what these bars mean. So that's the average temperature. Average, remember that's summer and winter. And you can see how it grows as you get out from the 20s to the 40s, 2040s to the 2090s. Next year, we start in the 2020s, okay? So when you see 2020s, that starts next year. So it's going to get hotter, and how much hotter remains to be seen, but it's going to be at least 2 or 3 degrees, but it could be 4 or 5 or 6 or 7 degrees, and that's just the average, which actually doesn't mean a lot. Most people experience temperature in terms of how many nights do I not sleep because it's too hot? How many days, do I get to go skiing? It's that kind of thing. The precipitation, the amount of rain that's going to come out of the sky, is pretty much, everyone thinks, going to be around the same. We don't know. We haven't resolved. Science has not resolved that. One thing people do think, though, is more of it's going to be coming in extreme forms. There's going to be more droughts and more floods. But the average might look about the same. So most of the effect of climate change that we now think about has to do with the way temperature is going to play forward. Does that make sense? Okay. And I think that's pretty common. People sort of know that. So what's that going to mean? Well, how many of you are skiers in the room? Some of you are. It's kind of bad news because the snowpacks are going to go away in a big way. Doesn't mean that Mount Bachelor and Mount Hood at the upper elevations won't have snow. It means that Hoodoo and Willamette and Ski Bowl and places that have historically been places that generations of Oregonians have gone to ski are basically not going to be there anymore. And I, as a skier, I mourn that as well. And the snowpacks are going to basically diminish. And if you go around the western U.S., the upper quadrant of the U.S. of the western U.S., we're going to get particularly hard hit by that. And the reason for that is that we have more of what people call snow at risk. And the reason is that most of our snow comes to us close to about 32 degrees. That is, and people at McKenzie Bridge know this very well. It's a wet, sloppy day here. It's 35 degrees, and it's snowing at the pass, okay? Right? And that's not a typical day. What that means, though, is that if you raise the temperature just a few degrees, you move from snowing at the pass to raining at the pass. In Colorado, most of the snow comes when it's 20 degrees or 15 degrees. And so if you move the temperature 3, 4, 5 degrees, it's still snow. So that's what the snow at risk is. The Cascades are going to really take it. The Sierras are too. So that's what these red colors are. Snow at risk. We're gonna feel it. Let's bring it home. Here's the McKenzie, modeled between basically, and this is a small climate change. This isn't one of the big ones. It's about a 2 degrees increase in temperature, and this is looking at how much snow will be around at what historically has been the peak of the snowpack at April 1, April Fool's Day. And basically these these cold colors are snow. And what you see is that with just a 2 degree warming, the snow just retreats all the way up into the high Cascades. Into the Three Sisters will still have snow, but the pass will not. And many of you who have lived here, I remember when driving up to Bend in the winter, those orange poles, there'd be winters where you would barely see the top of the orange pole, the 10-foot, 12-foot orange pole to mark the road. Now, it's not uncommon in the middle of the winter to have almost no snow at the top of the pass. That's what climate change is doing. Does that make sense? Is that consistent with others' experiences? Okay, so this, again, is all background. Now, a little bit of a change in direction. It's not just about the snow. Most of you have probably read or heard about this business of snow going away and earlier melt out and that kind of thing. But those of you who've maybe heard me talk before know that there's some other twists in here. And one of the take-home messages, if you remember nothing else about this talk, geology turns out to matter a big deal. Now, I am a geologist, so of course I think that. But it really does matter, and I'm going to try to convince you of that, at least in a simple way. It's not just about the snow, it's what the real estate people say, location, location, location. And what I mean by that is geology. Let's see how that plays out, okay? For a place like the McKenzie, it's all about the Cascades. And the Cascades turn out to be this wonderful set of mountains. I mean, beautiful, charismatic, volcanoes. But if you sort of step back to about a 30,000 foot view, they're an interesting place in terms of the globe, the whole Earth, because they're a place where you've got all this young volcanic rock. How many of you have been up to the top of McKenzie Pass, the Wright Observatory, looked out at all these sort of acres of fresh lava flows that look like they came out of the ground last week? That's young lava. Those are 3,000, 4,000, 5,000 year old lava. That's not usual. Not many places have that. And they don't have it where there's all this moisture coming in off the ocean with the winds blowing in from the west. And they don't have it at a temperate latitude, which means that, you can drive the pass in the summer even though it's snowy in the winter. And so this idea that there are mountains, they're full of these young volcanics, and they're near all this big source of water that's just bringing in, 10 to 12 feet of water. I mean, that's what it is. 120 inches of water up at the top. Picture that. That's 10 feet of water that comes in every year, and it falls on the ground in the high Cascades. That's a lot of water. There aren't many places on Earth like that. And that's going to foreshadow my conclusion about why this is such a special place and why climate change is going to make it even more so. Okay. I'm not going to dwell on this too much. Some of you have heard some of my geology talks, might remember this slide. But it is important for getting a sense of how the geography works, going back to that idea, location, location, location. Because it turns out that even in the McKenzie, the landscape has some very different flavors. There are the watershed is actually made up of these different geological flavors. And we're sitting right here, while you're eating your French fries, right at the boundary between two big geological regions. And the whole setup for this thing is driven by, and trust me, there's no test at the end of this, you don't have to remember this. But, there's an ocean, there are plates that are diving down underneath us as we speak. The plates get deep, the rock is under pressure, it melts, it comes up as volcanoes. It's been doing this for the last 30 to 40 million years, which if you look beyond where I can see, but if you look up at Lookout Ridge right behind us, those rocks up there, the lower rocks in there are about 30 million years old. And they all formed from this process of the slab going down and the magma coming up. The volcanoes are long gone. You're just looking at the residue, the throats of the old volcanoes, the lava flows that were laid down by those volcanoes. But if we go a little bit further up the road, the highway turns right at Belknap, right? Okay? And all of a sudden, you're going north, and to your left is all this older bit of the Cascades, like the ridge I just pointed out. And to your right are all these beautiful, young, volcanic flows, some of which are only a few thousand years old. How many of you have been up to Clear Lake? The Blue Pool. I mean, who hasn't been to Blue Pool? At least 50 times, right? Clear Lake. Clear Lake is the McKenzie River that was dammed by a lava flow that came out of the ground 3,000 years ago. Buried the forest. You can see the forest under the water. So this is a really active volcanic region, and these young volcanic flows are what fills up the high Cascades. Those of you are now sitting there going, why is he telling me this? This is about water. Why are you telling me all this? Well, it turns out that having this perception, this conception, is very important for understanding how this landscape, and actually, by extension, a lot of the landscapes in the Pacific Northwest work, and how they're influenced by climate change. So trust me, there's a thread that ties this all together. So we basically, the concept that you need to sort of have in your head is that there are these two flavors of landscapes. One is this old volcanic landscape, which we're in right now, and one is this young volcanic landscape, which is just to our east. And that the two are separated, as it turns out, by the fault, and actually the McKenzie River follows that fault. So when you're rafting down the McKenzie, on your left, going downstream, river left is the high Cascades, river right is the western Cascades, the old Cascades. So Why am I telling you this? Because it turns out that the way water moves in these two landscapes is completely different. Completely different. And in the high Cascades in particular, the water is almost always underground. Let me just flip back to this slide. Yeah, you probably can't see it. If you ever see a map or you ever see an air photo of the high Cascades, you'll notice there's very few streams. The streams just don't exist. And that's because the landscape's basically this layer cake, wedding cake of lava flow after lava flow after lava flow. And there just hasn't been enough time for the rivers to establish themselves, to cut their way down into it. And all that water, that 10 feet of water that we get, goes down into the ground. And I'll show you what it looks like, or what we sort of think. So that's the idea. Here are the high peaks of the Cascades. Here's this layer cake of rock, wedding cake. And all the water that's coming out of the sky is falling on this and running down and emerging as these absolutely amazing springs. So a few years ago, we had we did something for Oregon Public Broadcasting. And we had two undergraduate animators at Oregon State University who put this sort of Steven Spielberg-like notion. It's a little dark. But basically, it's the McKenzie. In fact, we're going to come over the ridge of the Western Cascades, and we're going to be looking up at Belknap Crater, okay, up on the horizon, all right? And those are all those young lava flows you see from the top, from D. Wright Observatory. So imagine yourself a raindrop falling out of the sky, and it looks like the lunar lander, but you're coming out of the sky. You're going to land on this lava flow, and what are you going to encounter when you get into the ground? You're going to be falling and following. This is a little bit of artistic license, but you're basically going to be following cracks and fractures and conduits and stuff you can't see that is taking and accumulating this water ever greater depths and ever greater volumes. So you picture this water coalescing together. Here's a side view of what it might look like. The water's coming down. These are individual lava flows. And you'll notice that each of the lava flows has a top and a bottom and a line. And those turn out to be places where water likes to go. It follows those lines. It accumulates at depth. And eventually, the volume of water, the pressure of water, and our old friend gravity combine to push this water out as the most glorious springs you've ever seen in your life. How many of you have seen Great Spring at Clear Lake? It's worth a stop. You can go around the trail. It's, they did a nice job. They captured this really. I think OPB paid him $100 for this, which was a bit of a bargain. But the McKenzie's basically fueled by these big springs, which is one reason it doesn't flood up here very much. It's the reason the water is cold. It's the reason there's bull trout in the river. It's the reason the river runs clear. It's the reason, it's the reason for Blue Pool. I can go on and on and on. And if you're interested in any of that, please ask me. I'll be happy to talk more about it. But it's not just the McKenzie that this matters to. So the picture you should have in your mind, if you're still with me, is that there's this young geology out there, and it has all these interesting ability to store water. Think of a giant sponge. This really is a geological sponge. And this drives all the rivers around here, whether or not they're tapped into this sponge or not. The big players in terms of the sponge are the McKenzie and the Deschutes. And just to give you a sense of how important the sponge is, this is a picture of the Willamette, the rivers that drain into the Willamette River. And they're color-coded by how much of the high Cascades, this young volcanic landscape that I just talked about, drains into them. And so the McKenzie's the poster child. About 40% of where the McKenzie joins the Willamette comes out of the high Cascades, 40% of the flow. The North Santiam has some, the Clackamas has some. The South Santiam has virtually none. And those of you who have ever driven the Highway 20 from Corvallis, say, through Sweet Home and then over the pass, know that the river looks completely different from the McKenzie. This time of year, there is no water in the South Sandium. You can almost walk across and barely get your feet wet. That's because none of these big springs feed into the South Sandium. And if you then go all the way to Portland, and what this plot is showing is the accumulation of flow. This is prior to any of the dams. And you see how the flow accumulates as you go downstream. And so here's the Coast Fork Willamette coming in. So this is the river moving downstream from Eugene to Portland. And as it goes, the flow increases. The biggest single increase is where the McKenzie comes in. It's a little bit more of the Sandium comes in, a little bit more of the Clackamas comes in. But basically, the way to think about it, and I feel very proud of this, is that the Willamette River in the summertime, certainly prior to the dams, was the McKenzie River, all the way to Portland Harbor. 30% of the river coming into Portland Harbor was the McKenzie. That's impressive. That's a lot. All right. Some of you are probably asking, what does all this mean about climate change? Well, this matters. What I've just described to you makes a big difference because it turns out that the way rivers are going to respond to the future depends a lot on whether they're being fed by this big groundwater system or by water that just falls in the ground, runs off, finds a channel, and is immediately delivered. And you can see that. This is what's called a hydrograph, and I'll be showing a few of them. A hydrograph is basically a graph that shows two things. On this axis, extra credit if you remember that was the x-axis. On this axis is time, and it could be days, seconds, hours. In this case, it's a year, okay? October to October. And if you look at the green line, that's Lookout Creek, which is just over the ridge from where we're sitting right now. And you see these spikes coming in from November to April. What do you think that is? I heard it. Storms. Exactly right. The storms come in, the river goes up, the river goes down, everyone around here. Thank you, Madison. You read my mind. Thank you very much. But look at the McKenzie coming out of Clear Lake. This isn't because of the lake. This is because in the wintertime, all that water coming out of the sky, all those storms, first they're being stored as snow, and secondly, it's all groundwater. It's being filtered through this big sponge, so there's no rises and falls. So even on a big stormy day, the river here might not rise more than a foot or two. It rose in April. I was watching it pretty closely, but it's not. This part of the river just isn't flood challenged. And when you look at it, if we were to all troop out to the bridge right here and look at the banks of the river, you'll see trees going right up next to the bank. You won't see bars. You won't see gravel. If you're a river guide, there's no place to eat lunch up here. I mean, there are no gravel bars. It's because there isn't this region, this piece of the river rarely floods, and it's because it's all going through the groundwater system. Does that make sense? You got that picture? Sort of, I see some heads nodding. Any questions? Let me just stop at that point. Any questions that have sort of piquing your interest at this point? Seeing none, I'll move on. Oh yeah, question, yeah.
Why would there be not more precipitation with higher temperatures and evaporation?
How that plays out, there is general feeling that the atmosphere will intensify in its cycling, which is where you get the more extremes. But whether that translates into more total precipitation, none of the models seem to suggest that. I mean, they could, but they don't.
But won't there be more evaporation with higher temperatures?
Yeah, there'll be more evaporation, and there'll be more plant usage of water, but how that plays out, it turns out to not, I mean, The models are not perfect, but they seem to be telling us that the amount of total precipitation, because again, total precipitation is, I mean, we're sitting on the western edge of the continent. Evaporation is all coming out of the ocean at this point. But whether we get it more as rain or more rain and snow doesn't seem, at least that's not what the models predict. We may get more big storms, big atmospheric rivers, but total will not be at least that seems to be the case. Okay, so I want to change our thinking back to climate change. I've just given you the background. I talked about water, talked about the background of water. I talked about a little bit about the geology and why location matters and how different rocks behave different ways. Now I want to bring it all together to say, so what does this mean about the future? And it turns out that in order to predict the future about water, it's not just about knowing that the snow is going to go away. It has to do with where things are going to happen. Because it turns out that the amount of water we're going to have in the future rests on four different things. And they all affect the shape of the hydrograph, that is, the shape of how rivers respond. The first thing is the climate, and I've already talked about that. Will the precipitation change? Will the temperature change, as we were just asked? Will the snowpack change? That all matters, and climate will affect all those things. Another thing that matters is the other thing I just talked about, which is how fast water gets to the river. Will it go very quickly, as we see in the Western Cascades, or it will have this very long, slow effect? And one thing I didn't point out is that all that water that falls out of the sky, it has to go somewhere. And so the reason why you can raft the McKenzie River in August or September is because it's being fed out of that groundwater system. The river just doesn't drop. That's all that water that fell out of the sky in the winter. So that matters. Another thing that matters is the vegetation. How much do the trees going to use? And the final thing that matters is something that we actually have some control about, is how people regulate water, primarily at dams. And all these things matter. So what's that going to look like? So how much precipitation falls? We're talking about the future now. So I'm showing you two sort of imaginary hydrographs, or projected hydrographs. That's time on the x. That's the amount of flow in the river on the y-axis, on the left. And so if we had more precipitation, we'd get a different hydrograph, okay? That's one example. If we have less, that goes down. Another thing that could happen, and this is the thing that a lot of people talk about, is the timing of when the precipitation comes. So if it comes as rain in the winter, instead of snow, which melts out in the spring, that's going to change the shape of the hydrograph too. That is, instead of having a snowmelt peak in April and May, which we're kind of used to, we're going to lose that. It's all going to come out in February and March because it's warmer. So that's another thing that climate change can do. A third thing that climate change can do, and the question sort of pointed to that as well, it can change the way vegetation uses water. That is, if it's hotter, the trees, it's not entirely clear because the trees are going to maybe turn on earlier in the spring, they're going to grow earlier in the spring, but trees also shut down when it gets too hot. So how that gets balanced out turns out to be a little tricky. And then the final thing is something that's not affected by climate change per se, but has to do with the landscape, which is the sufficiency with which water goes from being in the sky to being in the river. And that's that difference between the old Cascades and the new Cascades. So that all of these four things come together in climate change. So this turns out to be the most complicated graph I'm going to show you tonight. Okay? And it's, don't be hard on yourself if you don't get it. It took me a long time just to figure out how to do this. And I still don't fully understand the implication. But it gives a pretty good insight into what the future is going to look like around here. So this is a hydrograph. Again, hydrograph, time on the x-axis, in this case a year, starting in January. I'm being a little confusing here. This is January. These are winter storms, and that's summer, and that's the fall. And I'm comparing two landscapes. I'm comparing the high Cascades, just to our east, and the western Cascades, just over the ridge. You with me? Okay. There are two lines here. The black line in each case is what is today. Now, these are models. These are models. This isn't data. This is a computer simulation of the future. And what we do is we say, okay, we're going to model the river now. We're going to come up with a way where you basically what these models are, what they do is they say, you tell me the pattern of weather. You tell me how much rain is falling. You tell me the temperature. You tell me the wind. You tell me the sun. And I'll tell you how much water is in the river. That's what the models do in a nutshell. So the black is the current climate and the current model for, in this case, Lookout Creek. Let's look at Lookout Creek. That's the lower one. What do we see? We see the up and down, up and down. What's that? Storms. Exactly. Okay. We're following the black line. Then we get a little pulse here. What is that? Snowmelt. Extra credit. April, May, June, right? Okay. Then we go down. What's this going down, 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 down? That's the drought. That's what we're in right now. There's no rain, right? And notice that the system sort of runs out of water. There's very low flow. And that's why any fisherman here knows that if you go over to Lookout Creek or Deer Creek or Gate Creek or any of these, there's virtually no water in them. They basically run out of water. And then what's this over here? What happens over here? The fall storms. Storms kick in October again, right? And this place shuts down for the winter and everyone goes back to their homes. What's the future going to look like? Rain in the winter, more storms, maybe, rainier winters because less of it's falling as snow. Look what happens to that snowmelt peak. What happens? It goes away, right? And the river starts falling about a month earlier, right? Dives down. It's July, it's August. But what happens around September? It's about the same, right? We always run out of water here. And it's going to happen earlier, but by the time we get to August and September, you're not going to be able to tell the difference. Does that make sense? Because there's not storage in the ground. It all runs off quickly in that older landscape that's been chewed on and all the rivers have established themselves. Compare that to what's going to happen just upstream and in the main McKenzie River. You're going to have rainier winters. So here again, the black line is today. Here's a bigger snowmelt peak because we get more snow up there. It's higher. And then we get this sustained, this is today, following the black line, we get this long sustained flow that continues throughout the summer. That's why there's rafting on the McKenzie in the summertime. The flow is much higher because it's draining that big sponge. The future, blue line, rainier winters. We're not getting the snow, we're getting the rain. It's coming as storms, but notice that we lose our snowmelt peak. We start going down earlier, but at the end of the day, we still got water in the river. This is going to turn out to be one of the most important properties of the McKenzie River in the future. Fast forward 50 years from where we're sitting right now, and people are going to be going, "Thank you, McKenzie, thank you, McKenzie." Trust me, I won't be here in a meeting. But this is a big deal. But there's also another thing you'll notice if you look carefully at this slide, which is that we're going to see a much bigger change in the McKenzie than we are in Lookout Creek. And this turns out to be one of the most difficult things I've encountered to try to explain. That is, why is it that you can both have more water, continue to have water, but also have the biggest loss of that water? That turns out to be a hard thing to think about. But the best way I have to think about it is think about a bathtub that if you always have more water in the bathtub, you can always continue to drain it. This bathtub runs dry. We run out of water. And so the difference is going to be much more apparent, we think, in the McKenzie, even as it continues to have water. Does that make any sense at all? You have that idea? Can you picture that? So both things are true. It's one of these complicated ideas, but it's both. We will have water here in the future. It's wired into the landscape, but we're also going to lose water. And if we lose it, the Willamette loses it, the Deschutes loses it, and all the other rivers that are like this, the Rogue, the Klamath, the Sacramento, all the places that have water in the West are going to lose water. There's going to be less, just based on this alone. Because the snowmelt is happening earlier, the streams are draining earlier, and we're going to run lower in the summer. I'm going to stop there and ask if there are any questions. Because if you get that, if you have that picture in your head, you have a real essential thing. Make sense? I'm amazed. I mean, the Grateful Dead are happening over there. I'm glad. Thank you for staying with me. Okay, I'm not going to take too much more of your time, but I'm going to take a little bit more of your time. So just hang in there with me. I'm gonna breeze by a couple things just because I'm as usual going long. This is what we call the Navajo blanket, and in a nutshell, this is data. And without walking you through it, if you're a geek and you really want to learn, I'm happy to walk you through it. But this is actual data. This is actually 40 years worth of actually it's 50 years now of stream flow data. Each little pixel is a day. Those are the days of the year on the bottom and the years on the x-axis. And it's comparing the same two streams we just looked at, okay? I guess I am going to talk you through it. If we look at Lookout Creek, just over the ridge, the hot colors means no water, so the most hottest color is white, red, means no water. Starts in this is October now, but the same thing's true. Cool colors, blues, means lots of water in the river. So if you look over time, what do you think the speckling is? What are these blue speckles as we go from November to May? Storms, exactly right. Here are the storms marching in. How many of you were here in 1977 when the rains did not come in the fall? That's this red line here. The rains did not come until the spring. It was amazing. But that's basically, the speckling is here. Notice how here, when we get into the summer, within about a 2 or 3 week period, we get into the red. Doesn't matter how much rain came in the winter, wet winter, dry winter, we always get into the red about the same time. If we look at the high Cascades, we don't see that same pattern. We see much less speckling. It's all going in the ground. And there's this huge variation about where the stream is. A wet winter matters, a dry winter matters. And so there's memory in this system. This system runs out of both water and memory. It forgets whether it was a wet winter or a dry winter. Does that make some sense? You get some idea? So it's complicated because you've got these two landscapes sitting next to each other, and the rivers are responding to both. But they have these different flavors to them. But hang with me a little further, because what we've been able to do now is use this idea about when water comes, what form it comes, and how the geology plays into it to do all kinds of cool things. We can map out what places are going to have drought, and what places are going to be most sensitive to the future change in when water comes and how it comes, whether it comes as rain and snow. And it turns out these hot colors here, the yellows and greens, means more sensitive. So the Cascades are going to be sensitive, but they're going to be sensitive for different reasons. And I think I'm going to just blow through this because all I can tell you is it matters and it hangs together. And I'm happy at the end of this talk to sort of go back to it. How many of you were here in 2015? 2015 was like a window into 2080. there was no snow. It was what people refer to as a snow drought. The amount of rain, the total amount of precipitation that came, was about the same as a normal year, a little bit low. But there was no snow. I mean, in February, it was dry pavement, no snow all the way over the pass. So what effect did that have? So here, this is the normal range of snowpack. That's 2015. And that's what we think it's going to look like in 2080 around here. 2015 was a little window into the future. We were very interested in all kinds of things. Like I think I'm going to blow through all this, but one of the questions we asked was, how low will the McKenzie go? Because the model that I just presented to you suggests, hey, it should get pretty low. It should probably get to record low if it's like, what I said, where it's going to go down much further. That's what the prediction would be. It got pretty low. So this is the range of years, and this was 2015. How many of you were trying to get a drift boat down the McKenzie? I know Steve Schaefer's was. How bumpy was it, Steve? I timed that well, didn't I? Kind of like that. Had you ever seen it as low? Had you seen it as low?
I don't think so.
Okay. But it wasn't, but you could still do it, right? You could still get a boat down with caution, and it was you at the oars. I get it. 2015 was as low as we've been able to record. It was as low as 77 was. And it is pretty likely that the future has a lot more of those years, 2015, in store. So if you own a drift boat, you better put a good bottom on it. And then the other thing that happened, of course, and it's sort of happening this year, I don't fully understand it. The reservoirs are really low, aren't they? Are they unusually low? I haven't seen them myself, but are they low? They're pretty low, yeah.
They're doing projects.
Oh, they're doing, okay.
Engineers are doing projects.
So it has nothing, it's not a climate thing, it has to do with the project. Thank you. They're doing projects. It's our friends in the Army Corps of Engineers. But 2015, it was a bad year if you were running a marina at Detroit. It was a really bad year. And again, it's likely that this will be what we have into the future. And the other thing that will happen, of course, and this gets at some of the other questions, is, and this is sort of, I haven't really talked about floods, but there's also, you can play some of these same games and say, what's likely to happen in the realm of floods? And again, I don't want to talk about it, just because I'm running a little bit long. But I want to go back, I want to end with some thinking about, so what do we do about it? And I'm not talking about, buying a hybrid or, not getting on a jet airplane. There are lots of things people can do at various levels. But this change in the way water comes at us is going to change the way we live. It's going to change how we, how our cities work, how our agriculture works, not to mention how we recreate. Is there anything we can do that would mitigate this, affect it? And the answer is, we don't really know yet. We don't really know. But here are some ideas that I just want to throw out to you. And they're just as much speculation as science here. But what could we do? One thing I think we're going to need to do, and I think this will come home to this community more than most, is we have to start thinking about how forests use water. And there's a long history. I could happily give you an hour, and trust me, I won't, don't worry, talk about how forests and water work. But one of the things we've never really accounted for in our thinking is how much water gets used by forests. It's a really big number. In fact, forests use more water than all other uses of water combined. And to give you an idea, that's forest use at a national level in terms of cubic kilometers of water. Just to give you an idea, a cubic kilometer is about a sixth of a mile by a sixth of a mile by a sixth of a mile. Imagine a big block like that. It's a lot of water. That's over 1,000 cubic kilometers. That's water that gets sucked up by trees and transpired and returned to the atmosphere. It doesn't get lost. It's back in that thing called the hydrologic cycle, but it's not available for stream flow. And it's much bigger than agriculture or urban or anything else. And we're going to have to start thinking about that. And I mean, it's twice to three times the flow, the annual total flow of the Mississippi River gets pumped back up into the air by trees. And so we're going to have to start thinking about how trees use this water. And I'm not arguing that we should be like manipulating trees so we get more water. Point that I don't think I need to emphasize it too much in this community. We don't want our forests to burn down. We're going to have to manage water so that they stay wet. And how we do that is still a very infant science. We're going to have to start thinking about water as part of this sort of cycle of water. There's vegetation, there's fire, and they all talk to each other. And so what could we do? Well, one of the things we could do is start thinking of forests the way we think about our gardens. If you have a garden and you're trying to reduce the amount of water that your garden uses, what do? You mulch it, right? Could we do this to forests? Who knows? But it would make a difference, maybe. It turns out that there are many strategies. How we think about road systems, how we think about what trees we plant, whether we thin them or not, how we manage snowpack in the forest. These all matter in terms of keeping forests wet. So again, I'm not arguing that we need to manage forests for water downstream. And there are people out there who are arguing that. And I take issue with it. I think we need to manage forests for water so they don't burn up. Specifically managing water for the trees. And because the value of the forest to us is that it retains the forest. And the forest is going to be stressed. And if the forest is stressed, we're going to be stressed. So that's sort of the argument here. A second issue, I mean, just to give you an idea of what people are already doing. Wow. If you take your water, if your water comes from a glacier, as it does in the Andes or in Switzerland, people are going out with Mylar and covering the glacier to keep it from melting. I mean, these are like heroic measures. You know, people should have a big S on their T-shirts when they do this. But this is happening, and we're going to have to think about that kind of thing. Another thing we're going to have to think about is storing water in different ways. One of the ways is in the ground, and this is already being talked about. It's interesting. This is the technology that was present in Africa. That is present in Africa. People build basically sand pockets, specifically to store water, like a sponge. Okay, I don't think that's going to happen here, partly because we don't have any sand. But the idea of thinking of storage of water as a resiliency strategy is going to tap into that. That brings me to a hot topic: dams. There's a long history, and there's a lot we could say about dams. The history of building dams as heroic structures, dams as getting in the way of fish migration, which they certainly do in almost all cases. We have a history of the last 20 years of taking dams down. That's our Bruce Babbitt swinging the sledgehammer. But as we move forward, we're going to have to start rethinking dams, I think. And we're already doing that in the McKenzie. The way the projects that Steve was referring to, in many cases, have to do with temperature control. And it turns out the dam may be the only place we can significantly affect the temperature of rivers. So if you want to keep salmon in a river, by the way, the salmon was delicious tonight, if anyone had. But if we're going to keep that in the river, we're going to need to manage the temperature, and the dams turn out to be a place that we can do that. And so I'm actually anticipating in a funny way, and I just want to assure you, when I was a river guide, I had the banjo, and we sat around the fire and sang the song, "Damn the Man Who Dams Up the River." And everyone sang loud. But I believe we're going to have to rethink this. Not because I like dams, but because I think they're going to play a role if we're going to mitigate some of these effects. Okay. And then finally, and I really am just about done, we're going to have to think about how this plays out at larger scales. And I mean, let's take just as a scale the Western U.S. What we're sitting on here, going back to that argument I made before, that complicated thing about how we're going to have water, but we're going to lose water, which is a complicated bit of business. But we're going to have water. The Pacific Northwest, the volcanic terrains of the Cascades are going to have water even when other places don't. By other places, let's take, for example, Southern California. The Sierras do not have any of the storage. They have none of the sponge that we do. And that's going to really change things, in my view. It's going to change how people think, how people live, what people do. So what are people going to do? We could get better at how we use water. And that's already happening. And that's going to be driven by a whole set of economic forces. There are already people calling for more or bigger dams. I don't see that as a likely alternative, but we may find ourselves retrofitting dams. We may be doing what we did at Cougar to more dams, that is having temperature control structures, building up, retrofitting them for hydropower. One of the advantages to dams, is the fact that they're relatively clean energy. They can argue aspects of that, but basically they're clean. They're, from a carbon standpoint, they're clean energy. So there's going to be a push for that. And how we manage that is going to be an interesting story. A third thing, and this is the big boogeyman if you're in the Northwest, is they're going to steal our water. And anyone who's lived here knows that the fear of them coming for the water in the Columbia River and taking it to Southern California, it's you could do a good movie about it, or at least a song. Water turns out to be pretty heavy stuff, and so getting it over mountain ranges is not easy, particularly when energy costs you dollars and carbon as well. So I don't think the Columbia River is going to be sent to LA anytime soon. But what is happening is what's happening in California, where the water that comes out of the Sacramento is being transferred, instead of being allowed to go to the ocean the way it wants to, it's being transferred around the Delta and being sent to Southern California. That kind of stuff's going to happen more and more. I don't think it's going to happen here, but I think it's going to happen more and more. And the final thing is people are going to move.
Yeah.
And I think that's real. I think that we're going to find, and that brings me, if the water won't come to the people will come to the water. And it doesn't take, you don't have to be a scaremonger to think about what is it going to be like in LA or in Bakersfield or in San Diego, the 5th, 6th, or 7th year of drought, fire, and people wanting lawns for their kids to play on. They're going to come to where there's water. And where is there water? Right here. Right here. And it'll still be here. So it's this, if you run a wonderful business like this one, the future looks good. But if you look deeper into it, we're going to have to start thinking about this, because I really believe that the value of this landscape is going to be, we're sitting on a national treasure. This landscape is a national treasure. And it hasn't become apparent yet, but it will. Probably in my lifetime, but certainly in the lifetime of the youngins we see running around here. So, I want to leave you, though, with what we all should carry in our hearts, which is the image of this beautiful river, what it provides, how it sustains, what it gives us. And what I think we're really ultimately challenged is not just what can we take from it, but how do we give back to the landscape? How do we think ahead? How do we use these faculties that we're gifted with, born with, to make decisions now that will have real consequence and hopefully will make our children's lives a lot happier. Thank you very much for your attention.